Dear friends, Maths Aspirants Groups organizes online problem solving sessions on various topics to help the students who prepares for different competitive examinations. As a part of that series, today we have Ms. Nandana K. Vasudevan is with us to discuss some topics in the area of theory of matrices. Ms. Nandana, now pursuing Ph.D. at Amrita Vidyapeetham, Coimbatore. She completed her MSc from Cochin University of Science and Technology and qualified CSAR JRF. I would like to express my thanks and gratitude to Nandana for being with us. I welcome all of you to this event. Welcome, Nandana.
Thank you, sir. Good evening, all my fellow participants. So my topic is Ragnality Theorem, Eigenvalues and Eigenvectors. I think this is the topic left to cover in linear algebra. Rest of the topics that comes under linear algebra has been covered by one Miss Harsha Gopalakrishnan. She has discussed the theory part and other important results and all in her session very beautifully. So I'll be handling rest of the portion, which is Ragnality Theorem, Eigenvalues and Eigenvectors. So first we'll be looking at what is called Ragnality Theorem. So to state the theorem, we need to define what is called rank and what is nullity. We already have different definitions for rank, like it is the dimension of largest submatrix whose determinant is non-zero, then the number of linearly independent rows, number of linearly independent columns. We have so many definitions like that. So here we have a new definition in terms of something called the range space. That is, if A is an m by n matrix, the range space or image space or column space of A is defined as the set of all elements in Rm such that it is the image of some x in Rn under A. And when we are talking about this vector space, subspace concept and all, this range space is a subspace of Rm. And in terms of it, I can say that the dimension of a range space is the rank of matrix A. And similarly, we have something called null space of A, which is the set of all x in Rn such that Ax is equal to null matrix. And null space is a subspace of Rn, and the dimension of this subspace is called the nullity of A. And this is the famous Ragnality theorem, which is stated as, if A is an m by n matrix, then rank of A plus nullity of A equals the number of columns. So if we are given any two of the values, we can apparently find the other one which is unknown in it. Next, we have something called the row space and row null space. I would like to say something, that is, unless specified that it is row space or row null space, we'll be considering the usual range space and null space. Okay, so we'll be just defining it simply for understanding the theorem which is related to it. It looks much similar to the Ragnality theorem. That is, if A, the row space of A is defined to be the collection of all vectors in Rn such that it is the image of A transpose, it is the image of Y under A transpose. And row space, it is the subspace of Rn, and dimension of row space is also the rank of A. That is, dimension of row space or column space, both are rank of A. A matrix of order m by n, we have we have mainly four spaces associated with a matrix of order m by n. So first, we'll be discussing the most important two spaces, which are range space or image space or column space, all are the same thing. And second one is null space of A. So range space of A is defined to be the set of all B in Rm such that Ax equal to B for some x in Rn. And range space, it is the subspace of Rm. As we can see, it is a collection of elements in Rm. So the dimension of range space is rank A. We already have so many definitions for rank A, and this is similar other definition. Next is null space of A. It is a set of all x in Rn such that Ax equal to the null matrix. And it is a subspace of Rn, and the dimension of that subspace is called the nullity of A. Next, we have the theorem, which is the title of my topic, that is Ragnality Theorem. So if A is an m by n matrix, rank of A plus nullity of A equals number of columns, which is n. Next is rank nullity itself. We are defining it in a different way in terms of row. Till now we were talking about column, and now we are taking the next other two subspaces which are related to A. That is, if A is an m by n matrix, we have something called the row space of A, which is set of all B in Rn such that A transpose Y equal to B for some Y in Rn. And it is a subspace of Rn. When we were talking about column space, it was subspace of Rn. And when we are talking of row space, it is subspace of Rn. And it is also, the dimension of row space is also rank of A. That is, we can use either dimension of column space or dimension of row space to find rank of A. Then we have what is called the row null space of A, which is set of all Y belongs to Rm such that A transpose Y is zero matrix, and it is a subspace of Rm. So just like rewinding the previous definition of null space, it was a subspace of Rn, and row null space is a subspace of Rm. Then dimension of row null space is called row nullity. So I already said a point, I don't know whether it was audible or not. That is, unless we have been specified in the question that it is row null space or row nullity, we'll be only considering the nullity of A, that is column nullity. Okay, unless specified, it will be nullity itself. Next is a theorem which is much similar to the Ragnality theorem. If A is an m by n matrix, rank of A plus row nullity of A equals the number of rows, which is m. Next, we are going to the definition of characteristic polynomial and characteristic equation. From this point onwards, we'll be talking only about square matrices, which are of order n. Okay, even if it is not specified, it will be of order n itself. Okay. So A be a matrix of order n, the characteristic polynomial of A, denoted by chi A of x, is the determinant of matrix xi minus A. And characteristic equation of A is simply the characteristic polynomial equated to 0. That is, determinant of xi minus A equals 0. Next, we have a famous theorem which is called the Cayley-Hamilton theorem. That is, every square matrix satisfies its characteristic equation. So if we are given a matrix A and its characteristic equation is x raised to n plus a n minus 1 x raised to n minus 1 plus etc. plus a naught equal to 0. If I'm replacing these x by a, and since a naught doesn't have any x term with it, we'll be adding the term, adjoining the term I. That is identity matrix of order, same as that of A. So when I'm checking the equation, a raised to n plus a n minus 1, a raised to n minus 1 plus etc. plus a naught I, it will be 0 matrix. That is what it means, that every square matrix satisfies its characteristic equation. Next, we are moving to eigenvalue and eigenvector. So consider the matrix equation Ax equal to lambda x. And we can have values of x for which this equation has non-trivial solutions. Non-trivial solutions means x is not the usual null vector. It is It is the non-trivial vector. So the values of such lambda for which we can find non-trivial solutions is called an eigenvalue or a latent root. Usually we use the name eigenvalue or characteristic root. It is called a characteristic root because all those lambdas which are satisfying this condition will also be a root of the characteristic equation. And corresponding to each such lambda, I can find non-zero vectors x. And such x are called the eigenvectors or latent vectors or characteristic vectors, invariant vectors. It has so many names. Usually we call it the eigenvector or characteristic vector. So it's not compulsory that corresponding to an eigenvalue, there should only be one eigenvector. It can have more than one eigenvector associated with it. So when we are taking the collection of such vectors, that is set of all x such that ax equal to lambda x for some fixed lambda, it is called the eigenspace of that eigenvector eigenvalue lambda. Next, we have something called the algebraic multiplicity and geometric multiplicity. That is, algebraic multiplicity of an eigenvalue is the largest k for which x minus lambda power k divides the characteristic polynomial of A. That is, it is a formal definition of algebraic multiplicity. When I'm saying it in a more easier manner, if I'm taking a matrix A of order n, I'm listing all its n eigenvalues, then, and I'm picking one eigenvalue among it, say lambda. Then the algebraic multiplicity of lambda is the number of times it repeats. That is the algebraic multiplicity. And next, geometric multiplicity, it is the number of linearly independent eigenvectors associated with it. That is, when we are saying it more particularly, it is the dimension of the eigenspace associated with that eigenvalue. And we have one inequality, that is 1 less than or equal to geometric multiplicity of an eigenvalue less than or equal to algebraic multiplicity of the very same eigenvalue. Now, these are few points that we'll be using for doing problems hereafter. That is trace of a matrix. What is trace of a matrix?
Sum of the diagonal elements.
Sum of diagonal.
Yes, sum of diagonal values. So every matrix, when we are taking a square matrix, it will definitely be having a diagonal. So sum of those diagonal elements is called the trace of A. So when we are asked to find the sum of eigenvalues of a matrix A, it is not compulsory to find or calculate all the eigenvalues of A. Just add the diagonal elements of that matrix and you will be getting the sum of eigenvalues of that matrix. Similarly, product of eigenvalues of A is the determinant of A. Then if we are not given a matrix A, but its eigenvalues are given, it is of order, that matrix A is of order n and its eigenvalues lambda 1, lambda 2, etc. lambda n are given. Then from that we can calculate the characteristic equation of that or characteristic polynomial of that matrix. Like it is given by x power n minus sum of all the eigenvalues into x raised to n minus 1 plus sum of product of eigenvalues taken 2 at a time into x power n minus 2 plus etc. plus minus 1 raised to n product of eigenvalues. That is, next term will be, that is, first we'll be taking sum of all the eigenvalues. Next term will be sum of product of eigenvalues taken 2 at a time. Next term will be sum of product of eigenvalues taken 3 at a time. That is, we are increasing the number of eigenvalues. And finally, the last term will be product of all the eigenvalues. Right. So from this, we can just reproduce the result as chi A of x is x raised to n minus trace of A into x raised to n minus 1. That is just the thing that we have told now. That is, sum of eigenvalues of A is trace of A. So we are replacing that summation lambda I by trace of A, and rest of the terms remain. And last one, product of eigenvalues, I replace it by determinant of A. So where this second type, that is we have rewritten the formula of characteristic polynomial, where this will be helpful is when we come to small order matrices like 2 by 2 or 3 by 3 matrices. So if I'm considering a matrix of order 2, then its characteristic polynomial can be easily found by taking it as x square minus trace of p x plus determinant of p. And similarly, for a 3 by 3 matrix, its characteristic polynomial can be found as x power 3 minus trace of q into x square plus m11 plus m22 plus m33 into x minus determinant of q. That is, this computation, that is m11 plus m22 plus m33, is same as the sum of eigenvalues taken 3 at a time. Okay. So what is this m11, m22, m33? It is the minor of a11, a22 and a33. Can someone tell me what a minor is? Minor of an element.
Minor is
Yes.
determinant of the submatrix.
Okay, submatrix. How do you obtain that submatrix? That is what matters.
By
cofactor with sign.
One column and a row.
Okay, that is, you are missing a point there. If I'm finding the minor of the element Aij, I'll be finding the determinant of the submatrix obtained by deleting the ith row and jth column. Okay, it's correct that you're saying it is determinant of submatrix, but which submatrix? That is what is important. Okay, so don't miss that point when you're saying the definition of a minor. Okay, so that is characteristic polynomial for a 3 by 3 matrix. Next, if we know the eigenvalues of a matrix, we can also find the eigenvalues of its transpose, its power, its scalar multiple, any polynomial that is built using that matrix, and if it is invertible, its eigenvalues also. Okay, that is, if lambda is an eigenvalue of a matrix A, then lambda is also an eigenvalue of A transpose. Then lambda power n is an eigenvalue of A power n. K lambda is an eigenvalue of Ka. If P of A is a polynomial which involves the matrix A, then P of lambda is an eigenvalue of P of A. Then if A is invertible, then 1 by lambda will be an eigenvalue of A inverse. Okay. Similarly, if I have a matrix of order n, we can find the row sum and column sum of every rows, isn't it? I can find the row sum of first row, second row, etc., nth row. So if all the row sums, if first row is lambda and second row sum is lambda, etc., nth row sum is also lambda, that is, every row sum is lambda, then lambda is an eigenvalue of A. Similarly, if the sum of first column is lambda dash, sum of second column is lambda dash, etc., sum of nth column is also lambda dash, then lambda dash is an eigenvalue of A. Okay, actually, these are small points that you can use when you're doing the problems and all. Sometimes it may be a huge matrix, and maybe when you're adding the row sums or when you're taking the column sums, you can find that it is equal. So you can find the eigenvalue easily from it. Okay. Next, we'll be looking at eigenvalues of some special matrices. That is, we have some classes of matrices like symmetric, Hermitian, skew symmetric, orthogonal, so and so. So we'll be just looking at the pattern of how their eigenvalues appear. First one is diagonal matrix. So diagonal matrix, as we know, how does it look like? Only the diagonal elements will be present. Rest of the elements will be all zero. Diagonal elements may or may not be zero, but all the other elements except the diagonal elements will be zero. So I denote it by diag of d1, d2, etc., dn. Then the eigenvalues of A will be d1, d2, etc., dn itself. And the eigenvector corresponding to di will be ei, which is I have given it as row vector. It was a mistake. It is actually column vector. That is the column vector in which the ith element is only 1 and rest of the elements are all 0. So that is ei. And diagonal, when we are talking about diagonal matrices, we have special cases like zero matrix or null matrix, whatever, then identity matrix and scalar matrix. So when we are talking about null matrix, its diagonal elements are all 0. So from this we can say that its eigenvalues are all 0. Then when we are coming to identity matrix, its diagonal entries are all 1. So its only eigenvalue is 1, which is of multiplicity n, algebraic multiplicity n. And next, third case is that of scalar matrix. Scalar matrix is a matrix of the form ki, where k is any real number. So its diagonal elements are all k and all the other elements will be 0. So its only eigenvalue is k. And for all these matrices, that is zero matrix, identity matrix and scalar matrix, they all have eigenspace e1, e2, etc., en, where I have already defined ei, that is 1, 0, 0, 0, 0, 1, 0, 0, 0, so on. Okay. And we have one point that is, which is important, we'll be using it in questions, that is, if every non-zero vector in Rn is an eigenvector for a matrix A, if and only if it is a scalar matrix. Okay, that is, if the detailing is given that every non-zero vector in Rn is an eigenvector of A, then A is of the form Kin. And similarly, if it is of the form A equal to Kin, then every non-zero vectors in Rn will be an eigenvector of A. Okay, necessary and sufficient condition it is. Next is Hermitian matrices and
Hello.
symmetric matrices. Yes?
Yeah, how to prove the last one? I mean,
This statement, is it?
yes.
Giving the proof as such now, I think it will be a long way. Is it okay if I include it and then send the PPT to you later?
Yeah, okay.
Fine. Okay, next set of matrices is Hermitian matrices and symmetric matrices. So now we'll be having a notation that is A star. For a matrix A star denotes the conjugate transpose of that matrix A. That is, we'll be finding the conjugate of all the elements in A, and then we'll be taking the transpose of that newly obtained matrix, that is A star. So Hermitian matrix is a matrix A which satisfies the condition A star equal to A, and symmetric matrix is the matrix of the form A transpose equal to A. That is, in case of symmetric matrix, taking the conjugate is not required. The transpose alone will produce the same matrix. And we have the property here that eigenvalues of Hermitian matrices and symmetric matrices are always real, and the eigenvectors corresponding to distinct eigenvalues will be orthogonal. So when we are talking about orthogonality and all, it will be required to say dot product so and so. That is, if I have two vectors x1, x2, etc., xn, and y1, y2, etc., yn, it is orthogonal. These two vectors are orthogonal if x1, y1 plus x2, y2 plus etc. plus xn, yn is 0. So that is what is used here. If I take any two distinct eigenvalues of this matrix A, and if I take the eigenvectors of those eigenvalues, their dot product, that will be 0. That is what is called as orthogonal. Next is skew Hermitian matrices and skew symmetric matrices. Just like Hermitian and symmetric matrices, they are also related to their transpose or conjugate transpose. That is, skew Hermitian matrix is a matrix such that A star equals minus A, and skew symmetric matrix is a matrix such that A transpose equal to minus A. And for this, it will have the eigenvalues as either 0 or purely imaginary. Purely imaginary means any complex number, we write it in the form a plus ib. So here a will be 0. That is, it will only have the form ib. That is what is called purely imaginary. So the eigenvalues of skew Hermitian matrices and skew symmetric matrices are either 0 or purely imaginary. Next, we have unitary matrices and orthogonal matrices. Unitary matrices are matrices of the form A star A equal to A star equal to I. And orthogonal matrices are matrices of the form A transpose A equals A transpose equals I. And the eigenvalues of such matrices will be of unit modulus. Unit modulus in the sense, if the eigenvalues of A is A plus IB is an eigenvalue of a unitary matrix, then modulus of root of A square plus B square will be 1. That is what is meant by of unit modulus. Okay, so let me ask a question that connects 2 points that we have already discussed. If we are given a Hermitian unitary matrix, what can you say about the eigenvalues of such a matrix?
Eigenvalue is 1.
Okay, 1 and any other?
Minus 1.
Okay, very good. So it can be of 1 and minus 1. That is, being Hermitian, its eigenvalues can only be real. And when we are putting the condition that it is unitary as well, it is of unit modulus. So the only real values which are of unit modulus are 1 and minus 1. So they are the only possibilities. Okay. Next is idempotent matrices. So from here on, I think there are around 2 or 3 more type of matrices. So in these cases, you don't have to mug up the idea of eigenvalues. That is, here, idempotent matrices are matrices of the form A square equal to A. So there is a point to be noted. That is, if we are told that a matrix A satisfies some matrix equation. So when you are so that matrix equation will probably be of the form, if A is the matrix, it will be like A power n plus some an minus 1 power an minus 1, etc. A naught I. That will be the form of that matrix equation, whatever is given. So if it is told that the matrix A satisfies that equation, when we are solving that equation, the values that we are getting will be the eigenvalues of A. I'm not saying that all the eigenvalues will be obtained, but upon solving the equation, the real values that you are getting, it will be the eigenvalues of A. Okay, so when we're using that idea here, idempotent matrices are matrices of the form A square equal to A. That is, when we are solving this, when we are taking it as x square equal to x, what all are the values that satisfies it? Only 0 and 1. So eigenvalues are 0 and 1. Next one is something similar to it, that is nilpotent matrices. They are matrices of the form A power k equal to 0 for some k less than or equal to n, where n is the order of matrix A. Then it can have only eigenvalue 0. Okay, and there is one point that concerns this nilpotent matrix, that is, a matrix is nilpotent if and only if eigenvalues are 0. See, for these statements like symmetric matrices has eigenvalues real, then skew symmetric matrices have 0 or purely imaginary. If you want the proof for it, you can tell Vinod sir, he'll inform me. I can include that and then send the presentation to you. Okay, if it's required, you may inform him. Next, and this is the last type of matrix, which is involutory matrix, which is of the form matrices of the form A square equal to I, and its eigenvalues are 1 or minus 1. So always these two eigenvalues, no other possible eigenvalues are there. Okay. So that's all about the theory. Next we'll be going to problem session. And there is one thing that I would like to say. We have told about eigenvalues of few type of special matrices like diagonal, Hermitian, skew Hermitian, symmetric, skew symmetric, orthogonal, unitary, then nilpotent, involuntary, idempotent, so and so. We have said so many matrices. So there are questions being asked very directly about what are the eigenvalues of skew symmetric matrix. I have seen questions like that in many question papers, not just in JAM exam, like in CUSET exam, Hyderabad Central University, in so many such question papers, questions were directly asked. Okay, so please do keep these points in mind. They can be asked directly. So you need not miss your mark by doing calculations and all. Just remember these points. That will be enough. So can I stop my theory part and move to problems? Is there any area that I should repeat once again?
Ma'am, please repeat the A star.
Sorry, you're not clearly audible.
Ma'am, please repeat A star.
Which part? Hermitian matrix and all?
Yes, ma'am. How we define USA star?
A star, if I'm given a matrix A, then A star is the conjugate transpose of that matrix A. That is, it's not always compulsory that the elements, the entries of that matrix are real. It can be complex numbers as well. So if I'm given the entries of A, I'll be finding the conjugate of each of the element and then taking the transpose of that newly obtained matrix. Conjugate and then transpose. That is A star. Is it clear now?
Okay, ma'am.
Okay. And any other clarifications? Yeah, tell me.
Yes, ma'am. Actually, I
Ma'am,
wanted
does the
to ask
order
that
matter?
what
Like,
field
can
have
we
you?
take the... Okay, sorry. You go ahead, Sagar.
Sorry, one at a time.
Thanks. So I was asking that what field have you taken here?
Sorry?
Which field have you taken here?
Field, when we are talking about symmetric, sorry?
The thing is not here actually, but when you stated that determinant of a matrix is the product of its eigenvalues, then maybe it's a
Yes.
possibility that spectrum is not n.
We are considering complex numbers as
Okay,
the field.
that's
Okay,
all.
most general case we are checking now.
Yeah, thanks.
Okay. Okay, and the
Ma'am,
person who was left over.
ma'am, does the order matter? Like, if we take conjugate first and then transpose, or transpose first and then conjugate?
No, it does not matter. It results in the same matrix.
Okay, ma'am. Always, ma'am?
Yes, always.
Okay, ma'am. Thank you.
Always in the sense we are talking about only those n by n matrices. Right. Now we were talking about Hermitian and we were talking about order n matrices. Then it's okay.
Yes, ma'am. Yes, ma'am.
Okay. Any other clarifications?
मैम क्या जीरो मैट्रिक्स ऑलवेज डायगोनलाइजेबल होती है?
Sorry, you are not audible.
ये कह रहे हैं क्या जीरो मैट्रिक्स ऑलवेज डायगोनलाइजेबल होती है?
Zero matrix is always diagonalizable, yes. But I haven't included those topics because under JAM topic, this minimal polynomial, triangularization, diagonalization, all those things are not included. So why I excluded it from it. So zero matrix is diagonalizable. Okay.
Okay, thank you.
Right. Any other questions? If questions are over, then I'll move to the problem session.
Ma'am,
Yeah, tell me.
how can I prove that a matrix is a
continuous function.
Sorry, how can you prove that a matrix is?
Continuous function.
Matrix is a continuous function. Oh my God. You are asking something which is totally detached from the topic that I am taking now. Is it okay if I include it in my PPT later and then let you know?
Yes, ma'am. Yes.
मैम ये जो आप मतलब पढ़ा रही हैं इसका डीपीपी मिल जाएगा हमें?
Sorry, can you say in English?
सॉरी मैम, मतलब इंग्लिश में थोड़ा लैंग्वेज प्रॉब्लम मतलब.
It's okay. You can say.
Ma'am, he's asking that will we get the PPT of what you are teaching right now?
Yeah, I'll send it to Vinod sir. He'll be forwarding it to you.
Okay.
So shall I move to problem session?
Yes, ma'am.
Okay. Is my screen visible now?
Yes.
Yeah, ma'am. Yeah.
Okay. So I'll be showing the question first. Any of your answers are most welcome, be it right or not. This is just a discussion session. So don't feel bad thinking that your answer may be wrong. Okay. And let me say one more thing very frankly. When I was preparing questions for this session, I found it really hard to pick up some questions which are different or there is something difficult in it. Because almost all the questions that were relating to this topic were almost directly applying questions. That is, all these results that we have looked like trace, determinant, and few other results and all. Most of the questions we were directly applying it. Okay, so finding hard questions in this topic was a tough job. That is, if you are looking at the theory part very clearly, it will be very easy for you to score mark in this topic. Okay, so the questions that I am going to present may seem easy for some of you and may not be easy for some. So anyhow, we'll be taking it as a discussion session. So this is the first question, that is, let A be the matrix. Yes?
Can I answer it?
Yeah, one sec. I'll just read the question and then you can start. Okay. So let A be the matrix A minus 1, 4, 0, B, 7, and 0, 0, 3 be a matrix with real entries. If the sum and product of all the eigenvalues of A are 10 and 30, then A square plus B square equals. Okay. So, and 4 options have also been given. This was the question asked for JAM 2014. Yeah. Now your answers are most welcome.
Nandana, many of them are commenting answers in chat
Sir,
box.
I saw it just now only. Okay, so many of them have commented 29. Okay, and one person has commented it as 40. So since the person who has commented it as 40, do you have something to discuss? Because you have got something different from the answer that all the others have commented.
Yeah, in this A is it's an upper triangular matrix, and in an upper triangular matrix, the diagonal entries are the eigenvalues, and we are given then. Oh, sorry. I think I got.
Yeah, just wrong. Proceed. You don't have to stop.
I got something wrong.
Probably computation error. No worries. Okay. So the answer is 29. Okay. Anyone may give the explanation for it.
Yes, ma'am. Trace of A is equal to sum of the eigenvalues. That means A plus B plus 3 is equal to 10, and product of eigenvalues is equal to date of A. That means 3AB is equal to 30. And we can calculate A minus B, and if we complete the calculation, we may get a minus b is equal to 3, a plus b is equal to 7, that means 2a is equal to 5, that 2a is equal to 10, that means a is equal to 5, and b is equal to 2, and a square plus b square is equal to 25 plus 4 is equal to 29.
Yes, very good. He has given the complete explanation of it. So that's it. That is, here the only point that is to be noted is that for an upper triangular or a lower triangular, beta triangular matrix, then its diagonal values will be the eigenvalues of that matrix. I have told only about diagonal matrices. So even in case of triangular matrices, the diagonal entries will be the eigenvalues. So here A, B, and 3 are the eigenvalues of A, and we have the detailing of sum of eigenvalues and product of eigenvalues. So just as he has explained, a plus b plus 3 is 10 and 3ab product is 30, and upon computing we get it as a5 and b2, or the other way, that is a2 and b5. Either way it is, on computing we'll get it as a square plus b square to be 29. So that is the right answer. This is the second question. That is, M is a matrix of order 3 with real entries, and it satisfies the equation given by m square equal to m plus 2i, where I denotes identity matrix of order 3. I take its eigenvalues to be alpha, beta, and gamma, such that its product is minus 4. Then what is its sum? That is the question. So it's a numerical answer type question. Options are not given. So answer suggestions can be posted in the comment box, or you can unmute and say. Yeah, you can take 2 or 3 minutes to compute it. If you make your computations,
ma'am, what the value of मतलब कि alpha, beta, gamma?
It's not given. That is a question you have to find. Only alpha, beta, gamma product is given. You have to find the sum of those eigenvalues.
मैम न्यूमेरिकल वैल्यू शो नहीं हो रही है, एग्जैक्ट शो नहीं हो रही है. -4 है कि +4 है?
-4.
ओके मैम, थैंक.
The matrix is not given, only its product is given and an equation that satisfies that matrix. Is there any quick answers? We cannot lag too much.
Ma'am, 3.
3 ma'am.
Okay.
Alphabetic.
Any other answers?
3.
Okay. Can we fix with the answer 3 and then proceed? Okay, we'll check. That is the point that I told earlier when I was talking about that idempotent matrix and all. So it is given that m square equal to m plus 2i. That is, the given matrix satisfies that equation. So if I'm making it of the form x square minus x minus 2, which is something equivalent to that of the equation given. Okay, so on solving it, I get the values to be x equal to 2 and x equal to -1. So this 2 and -1 will always be eigenvalues of m. Okay, that is one point to be noted. So 2 and -1, I take it to be alpha and beta, and we are given that its product is -4. So from that, after all the computation, I get gamma to be 2. So after all those works, I get alpha plus beta plus gamma to be 3. So 3 is the right answer.
Ma'am, how is that there are 3 eigenvalues of a matrix and the annihilating polynomial has degree 2?
It's not that annihilating polynomial has degree 2. It's not like that. If we are given that matrix satisfies this polynomial which is given, You don't have to go to that annihilating polynomial so much hard things and all. It's just that
still,
if
it's kind of absurd actually that the degree of annihilating polynomial must be at least the number of eigenvalues are there, isn't it?
See, we have something, see, 2 is of multiplicity 2, right?
Yeah.
That is, eigenvalues are 2, 2 and minus 1. So 2 is of multiplicity 2 and minus 1 is of multiplicity 1. So isn't it possible that this is the minimal polynomial of that matrix?
Yes, got it.
Okay.
Thank you.
Is it clear now?
Yeah.
Okay. Any other confusions? Okay. So I assume that there is no more clarifications required. This is the next question. So let P be a 4x4 matrix with entries from the set of rational numbers. If root 2 plus I, where I is root of minus 1, it is a characteristic, actually it is characteristic, okay, it's a root of characteristic polynomial of P, and I is the 4x4 matrix, that is matrix of same order as that of P, then which among these will be satisfied? That is the question. So I think computing the whole thing will be time consuming. So can someone tell me what the idea that will be used in solving this question?
Since P is a 4x4 matrix and the entries are from rational, in particular from reals, and root 2 plus I is a root of characteristic polynomial, then root 2 minus I is also a root of characteristic polynomial.
Okay, very good.
Then we can,
क्योंकि रूट्स अकर करते हैं स्क्वायर में.
then we can.
Please don't interrupt. Just one at a time.
Sorry. Then we can take.
Okay, so if root 2 plus I is a root, then root 2 minus I will also be a root. Okay. Then what next?
Take the polynomial x minus root 2 plus I into x minus root 2 minus I.
Okay.
And after solving, again after some computation, then we will take again a square. Then from this product we got x to the power 2. Now we need x to the power 4, so we again square, and this must this equation satisfied by P, and after inserting P we get.
Okay. Any other answers? Someone else was speaking in between. Okay, so the one who said the answer just now, first step of what you said was right. That is, when root 2 plus 1 is a root, then root 2 minus 1 is also a root. That is, these complex roots appears in pairs, how conjugate pairs. We have something very similar. That is, when we have these root 2, root 3, such things, that is, if a plus b root 2 is a root, then a minus root 2 is also a root. There is a result like that as well. That is the idea used here. That is, if root 2 plus I is there, then root 2 minus I is also there. Similarly, I am taking the pair along with that radical. That is, I minus root 2 will also be there. Then minus I minus root 2 will also.
But in the second case, the A and B is from real number, right? Then we are taking A plus B root 2 as a, conjugate pair of A minus B root 2.
I didn't get you.
Okay, you are saying assume A as I and B as 1, then I minus root 2 is also a root, right?
Yes.
But in that part, if a plus b is a root 2, sorry, if a plus b root 2 is a root, then a minus b is a root, a minus b root 2 is also a root when a and b are real, I guess, right?
Yeah, it's true. But when I was going through it in detail, when it comes as imaginary, that it when I is included also it holds.
Okay.
Okay. So that's where the point lies in this question. So rest of the part is simply computation. Okay. That is, we are taking these as the factors, that is x minus first term, x minus second term, then the regular computation. We are grouping it as a plus b into a minus b and all step by step. And after all the computations, what we get is x power 4 minus 2x square plus 9. That is the characteristic polynomial of x. So using Cayley-Hamilton theorem, we can say that this matrix P satisfies its characteristic equation. That is P power 4 minus 2p p power 2 plus 9i is 0 matrix, from which I get p power 4 equals 2 p power 2 minus 9i. That is option 3. Any
what
other
was the use
doubts?
of rational numbers being given there?
Sorry?
What was the use of the entries being given as decimal?
Entries given as decimal. I didn't get you.
Rationals. What was the use of entries given as rationals in the question?
I'm sorry, I'm not clear I'm not understanding what your doubt is.
In the question, it is given that the entries of the matrix is from rational numbers.
Yes.
So what was the use of it here?
That, given it as rationals or reals, that is not what matters in this question. Okay, it is just a detailing of that matrix. That's all. It is not necessary that if the entries are all rational, then the characteristic roots will always be real. It's not set like that. Okay, so it's just a detailing about that matrix, nothing more.
Okay.
Ma'am?
Yeah.
How can you conclude that negative I, negative root 2 and I minus root 2 are also the eigenvalues of P?
Eigenvalue.
Yeah, that's what I said just now. One sec. Are you talking about these two eigenvalues?
Yes.
Yeah, that's what I told just now. That is, if a plus b root 2 is is a root of some polynomial, then a minus b root 2 will also be a root of that polynomial. So we have usually seen that result for a and b to be real numbers, but later on when I was going through some details, I found that it holds for I also. So that is how we have taken it as pairs. Is that okay now? Am I audible?
I'm not convinced with this.
Sorry?
I'm not convinced with this last two eigenvalues. How this comes?
Like, now how far I can give the explanation, I don't know. I have given it to my largest extent.
Let me tell something, Nandana.
Yes,
I think possibly it may be due to the fact that complex roots as well as surds will occur as conjugate pairs. That may be.
Yes, that's the result. So I have already said that, but I don't know whether they have got it as such or not.
Okay, Nandana, you can move on.
Okay, sir. This is the next question. That is P equals 1 minus 3, 3, 0 minus 5, 6, and 0 minus 3, 4. Then what is the product of eigenvalues of P inverse? That is the question. This is also a numerical answer type question. We don't have options. You'll have to compute it all by your own. So can we have the answer suggestions, please?
Is it minus 1 by 2?
Minus 1 by 2. Okay. Any other answers? Okay, the person who said minus 1 by 2, can you just explain what idea you have used?
The product of eigenvalues is determinant. So P inverse, if a determinant is not zero, non-zero, then P inverse is a product of the is P. Eigenvalues of P is let it be product is, if it is determinant, then 1 by P inverse is 1 by P, 1 by determinant. That is here the determinant is minus 1, minus 2. So the product of eigenvalues of P inverse is minus 1 by 2.
Yeah, sure. That is one way of doing it. Very good. And any other ideas that by applying these results that we have already taken?
Ma'am, I started with sum of each row is 1, but couldn't, like the method he did was much shorter.
Yeah, that's right. But I was just asking for a secondary option. That is, we have told some results and all using eigenvalues. So we can use it somewhere, right?
The eigenvalue of P is minus 1, 1 and 2. And therefore, the product of P inverse, eigenvalues of P inverse is 1, 1 by 2 minus 1. That means, therefore, the date value of P inverse is equal to half minus 1 into 1. That means minus 1 by 2.
Okay, good. So I have used the idea of eigenvalues actually. That is, we have been, just as he told, when we are adding the rows, all the row sum is 1. So 1 will be an eigenvalue of it. Then we have the trace. We look at the trace of it, which is 1, minus 5, 4. Or just like if we are, instead of product of eigenvalues, if you are asked to find the eigenvalues itself of P inverse, also you can use the same thing, right? So 1, minus 5 and 4. So trace is 0. So sum of every row is 1. Thus 1 is an eigenvalue. And rest of it we have as lambda 2 plus lambda 3. That is sum of rest of the other eigenvalue is minus 1. And again, applying the result of product of eigenvalues, we get it as minus 2. Then the usual computation, that is eigenvalues of P can be obtained. Then eigenvalues of P inverse is just the reciprocal of the values that we have got, and product is just multiplying it. Yeah, finding the inverse of, 1 by determinant of A, that is one easy way. Yeah, when you are writing for exam, that will be enough. But I was just applying what we have already discussed. Okay. Whichever way is less time consuming, you can opt for it. That is. Okay. Next question. It is not from JAM exam. It was given for Delhi University entrance exam for 2015. We have a 2 by 2 matrix, 1, 2, 2, 1. And we are given an expression. We are asked to find the rest of it. The RHS of that expression is asked. So any answer suggestions or answer ideas, how you can solve it? Any answers, or should I proceed to the answer directly?
Two a plus 3i.
2a plus 3i. Okay. Yeah, one of you has answered it as Cayley-Hamilton theorem also. Okay, so we'll see how we are applying it. That is, corresponding to this matrix, we can find its characteristic polynomial to be x square minus 2x minus 3. So, using Cayley-Hamilton theorem, a square minus 2a minus 3i is 0, and from which a square is 2a plus 3i. And substituting it in the equation that was given to us, it will directly yield 2a plus 3i, which is option 1. Okay, very good. Okay, this is the next question. It was asked for Hyderabad Central University 2011 exam. We are having a matrix, real matrix of order 2, and which of the following statement is true? That is, all entries of A square are non-negative, all eigenvalues of A square are non-negative, determinant, and trace. So nothing is asked about A, everything is about A square. So do we have any answers?
Ma'am, option 2.
Option
2, ma'am.
Okay. That is, determinant is non-negative.
Yes.
Okay. One of you has asked as option 3. Okay. Any other answers?
Option 2 is false, I think.
Okay. And okay. Shall I move to the answer? So let's keep the last 3 options aside. We'll look at first question, that is square of the matrix. All the elements in the square of A is non-negative. So this is one counter example for it. You can find other counter examples as well. So this is one such A with real entries, but its square, we obtain it as minus I. So its entries are not non-negative. Next, we'll be checking at eigenvalues. So when we are looking at eigenvalues, we'll definitely get what is called the trace and determinant. It follows along with it. So let us take the eigenvalues of A to be A plus IB and A minus IB, because they occur as conjugate pairs. So we'll check the eigenvalues of A square first. So it will be A square minus B square plus I 2AB and A square minus B square minus I 2AB. So here it's not necessary that it is non-negative. Maybe if both A and B are non-zero numbers, then it can be complex as such. So it is not non-negative. So we can skip that option D, that eigenvalues of A square is non-negative. Then comes trace. So trace, when we are talking of it, it's just the sum of these 2 values, trace of A square, which is A square minus B square, which again need not be non-negative. It depends on what value A and B has. And finally, it is determinant, which is product. So upon computation, we get that its value is A power 4 plus B power 4 plus 2A square B square. So whatever be the value of A and B that we have taken, it will be non-negative. Okay. So the answer is
determinant
is non-negative. Any clarification?
I think the solution is a bit incomplete, as you have taken eigenvalues to be A plus minus IB, because here you have taken eigenvalues as complex, but eigenvalues can be real as well.
Yeah, you take B to be 0. That will be enough, no?
Ma'am, but that will make both eigenvalues as A. So eigenvalues can be X, Y as well.
Sorry?
And if we take B as 0, then that will make both the eigenvalues as A.
Yeah, okay.
So,
but what I was trying to say is that if we are taking a real case, when it is a real case, these eigenvalues are obvious that it is non-negative. Its trace, its determinant are all trivially non-negative.
Yes, ma'am. Yes. What?
Isn't it? That is the reason. It's not that I skipped that point. It was just that it is trivial. So why I left it off. Okay. Thank you for reminding me. There may be students who are having such a doubt. Okay. So I took the complex case to take it in a more general way. That's all. Okay. So is there any other doubts?
No, ma'am.
Okay. So this is the next question. We have a 3 by 3 matrix given, and we are asked to find the largest eigenvalue of A.
4, ma'am.
Ma'am, 4.
4. Okay. 4. So I think that was much easy answer question, it seems. So that's it. That is the row sum of every row is 4, and its rank is 2. So one eigenvalue will be 0, and the other eigenvalue from rest of the computation we get it to be -4. So among these, 4 is the largest eigenvalue. That was an easy question, is it? Okay, next one. We are given that M is a matrix of order n with m square equals 0. Then what can we say about eigenvalue of m plus alpha I, m minus alpha I minus m? That is the question. Any suggestions or any ideas to be shared?
Option D, ma'am. Option B and D.
B and D.
No, actually B only.
Actually, you should read the option. It's already given. It is the only eigenvalue. So you cannot
Actually,
say
B
two
only.
options here anyhow. Okay, B. And any other answers?
Since m square is 0, so m is the nilpotent matrix of index 2. That means all the eigenvalues of m is 0.
Okay.
And we know if lambda is the eigenvalue of m, then p lambda is the eigenvalue of pm.
Yes, very good. That's the idea used. That is, if m square, we are given that m square is 0 matrix, so m is nilpotent. So 0 can be the only eigenvalue of of m. So if lambda is an eigenvalue of m, we are taking a polynomial in m, then the polynomial corresponding to that, the eigenvalue corresponding to that polynomial involving that matrix will be same as that using that eigenvalue. So using that idea, if m, when we are considering m plus alpha I, it has as eigenvalue 0 plus alpha, which is alpha. Then m minus alpha I, it will have minus alpha, and alpha I minus m, again alpha, which means both m plus alpha I and alpha I minus m both has eigenvalues alpha only. So answer is option 2. Very good. This is the next question. That is, P is a real matrix of order 2, such that every non-zero vector in R square is an eigenvector of P. Then, if lambda 1 and lambda 2 are its eigenvalues, and we are given a matrix equation, then which of the following are true? These are true. That is the question. So we have already told that point when we were discussing the theory part. So any answer suggestions?
So P becomes a scalar matrix.
Yes, very good. And rest, any other things that you can connect from the details that have been given? Actually, that is the most important thing that is to be noted in this question. Rest of the things follows. I'll show the answer. That is, since we are given that every non-zero vector in R square is an eigenvector of P, P will be of the form Ki. So when we are substituting it, we get that root K equal to 2 and K root 3 equal to T, it is given as for some T belongs to R. So we need not consider that. We'll be looking only at this part, that is root 2 K equal to 2, from which we get K equal to root 2. That is, this P is the diagonal matrix with diagonal values root 2, root 2, from which we get lambda 1 into lambda 2 is 2 and root 2 is an eigenvalue of P. So that is the only point that is to be noted in that. That is, if every non-zero vector in R square is an eigenvector of P, then P is a scalar matrix. Okay. Any other clarifications? Okay. This is a question asked for JAM in 2016. That is, P is a 3x3 singular matrix such that PV equal to V for a non-zero vector and P of 1, 0, minus 1 equal to 2 by 5, 0, minus 2 by 5. Then which of these will be satisfied by P? The matrix P is not given, but few details about P has been given. So is there something that you can say about which equation will be satisfied?
Since P is a singular matrix, then 0, 0 must be an eigenvalue of P.
Yes.
At least. And PV is equal to V, that means 1 is also an eigenvalue of P.
Yes, very good.
Yeah, and now from these 2 points, we can get that third eigenvalue. No.
Just one more point left.
Yeah.
There is only one more point that you have left.
Okay. Minus 2 by 5 is also an eigenvalue.
Yes, that's it. That is, we have been given the details of eigenvalue in the question itself. That is, it is singular, so 0 will be an eigenvalue. PV equal to V for some non-zero vector, which means 1 is an eigenvalue of it. And the third detailing, from it we get that 2 by 5. When we are taking 2 by 5 outside as a common factor, we will be getting it as P into 1, 0, minus 1 equal to 2 by 5 into 1, 0, minus 1. So 2 by 5 is the third eigenvalue of P. And then we are just substituting it and finding out, we get the value to be, yes. So this is just the same thing that we have used in the theory part. That is, first one is sum of eigenvalues 0, 1 and 2 by 5, which is 7 by 5. Then 2 by 5 will be the next one, that is taking pairwise. We are taking the sum of products taken 2 at a time. So which is, we get it to be 2 by 5, and finally the determinant. Since it is singular, determinant will be 0. So we don't have a constant term there. And upon substituting it, substituting P for it using Cayley-Hamilton theorem, we get it as 1 by 5, 7P square minus 2P. That's all. So the person who answered it, very good. And this is the last question that I have got to discuss, which was asked for JAM 2017. We are given a 4x4 matrix, and if alpha, beta, gamma, and delta are the eigenvalues of this matrix, then we are asked to find the sum of squares of these eigenvalues.
It is actually nothing but a companion matrix.
Sorry?
It is nothing but a companion matrix.
Okay.
So we can get characteristic equation from the last column.
6, ma'am.
Okay, that was a good idea. Okay, using idea of companion matrix. Okay. So for people who doesn't know the idea of companion matrix, what is to be done? That is the next question. Someone said answer 6. Do you have an idea other than the idea of companion matrix?
Ma'am, we can square this matrix and then check its trace.
Squaring the matrix and checking the trace. Okay, that looks good. Then it's a 4x4 matrix. Okay, that is also easy. I think the computation that I have used is lengthier than what you are saying. I feel so. Okay, that is also a good idea. Any other option? Okay, so I think I should move to the answer. I have used the idea of that characteristic equation coefficients. Yes, when we are using the idea of companion matrix, we can easily find the characteristic equation. But those who are not aware of what a companion matrix is, you have no other option than to compute it. That is, I take alpha plus beta plus gamma plus delta whole square. So upon simplification, just grouping and simplifying, I get it as alpha square plus beta square plus gamma square plus delta square, which is what we need. And rest of it is twice the sum of product of eigenvalues taken 2 at a time, right? So when I'm transposing the term, I get it to be alpha plus beta plus gamma plus delta the whole square minus 2 into that rest of the term. So from this, upon computation, I get the characteristic equation to be lambda power 4 minus 2 lambda cube minus lambda square plus 2 lambda. From which, so according to the equation that we have looked, this 2 will be the trace, that is alpha plus beta plus gamma plus delta. Then here what we have is plus minus 1, which is the sum of product of eigenvalues taken 2 at a time, which is minus 1. Then this value is just sum of product of eigenvalues taken 3 at a time, which is not required. We only need these two terms. So we get alpha plus beta plus gamma plus delta is 2, and the other one is minus 1. And upon substituting it in what we have obtained earlier, we get it to be 6. So that is the approach that I followed. And yes, when it comes to this topic, you can use different ways. Like, since it is things that involve trace, matrices and all, you can use the properties of trace and matrices also. So there are too many ways to solve the same question. Like when we were talking about this question, that is, we were asked about product of eigenvalues. So it is enough to find the 1 by the determinant of P. That is enough. Or the way that I followed was using the idea of eigenvalues. And if you sit and find the inverse of that matrix and then find its eigenvalue and then find its product, that is also correct. It is nothing wrong. But what matters when you are writing such exams is time management. So whichever you find it easy to manage your time, you can opt for that method. Okay. So only thing that I would just remind you once again is that these points, that for each type of matrices, what kind of eigenvalues they have. Is it real, purely imaginary, 0, 0, 1, or -1, whatever. So such things, you need to be very thorough about it, because there are direct questions asked. So you can simply just, you don't have to do any computation, just pick the answer. So do be clear with those topics. So that's all, sir.
Thank you, Nandana, for this discussion session, for this problem solving session on matrices. Dear students, as you know, linear algebra, yeah, of course, matrix theory as well as finite dimensional vector spaces. There will be lots of problems from these areas for either for your JAM exam or NET exam. And you know, all these things can be done but if you have much time, but in an examination, effective time management is very important. So you have to be very aware about the question types and all that. You have to practice, then otherwise you may not be able to do it in an examination. So you have to exert more care in studying this type of problems, because you know there will be lots of problems from this area. So now it is the time for discussion. Okay, you can ask any of your doubts, or you can express your comments here.
Sir, I'll include some of the proofs for that eigenvectors and few such things that they have asked, and I'll send the newly produced PPT to you.
Okay, we can share it with them.
Okay, sir.
Okay, dear friends, feel free to interact. Our sessions are actually giving such an opportunity to you also. Take this opportunity to interact with the, yeah, all we are from the area of mathematics, so we can discuss something. So feel free to interact.
Yes, sir. Thank you so much. It was quite a wonderful session indeed. And yeah, I'm so glad that you are organizing all this without any cost. Like, obviously, many of us has joined coaching, but apart from that, as well, we are getting this extra help is a blessing in disguise, obviously. And the only thing I wanted to ask was, can you please guide us in this late time of examination? Like, the exam is just around the corner, and can you please give us a few tips?
Sagar, can you introduce yourself?
Yes, sir. Sir, I am Sagar. I have pursued my BSc Maths honors from DU only, and these days I have taken a drop of a year for preparing for JAM Maths only.
Okay. So, yeah, JAM examination, I think only around 80 or 85 days left out. So now it is actually for the time for revising the things and revising the concepts and practice more and more problems. That is the only thing that you have to do. Okay, I think Nandana will add something more about preparations.
I'm not that big an expert to give such tips and all. Like Sir said, just go through the more problems, and yes, don't go behind too much of proofs when you are preparing for exams, because proofs are not usually asked for exams, since they are numerical answer types or multiple choice questions. It's enough to look at results and theorems more precisely. So read more, do more. That's all.
Yeah, remember the words of Helmholtz, the only way to learn mathematics is to do mathematics. So practice maximum problems and as well as revise the concepts and the results. Okay.
Okay, sir. Thank you so much. Thank you.
Okay, others. Okay, many of them are writing in chat box. You can directly unmute yourself and talk also.
Good evening, ma'am. My name is Vaishnavi. I am a third year student from St. Paul's College, Karamasheri, Ernakulam. Really, I missed the class a little bit because I was a little busy. But I tried to get into the class as much as I can, and the last section, last 3 problems was good. You took it well, and it was really I really missed the class, and I would definitely see the video, recorded video. And thank you for your class. Thank you so much, ma'am.
Yeah, welcome.
Thank you, Vaishnavi. This.
Hi ma'am, my name is Kavya. I'm from Bantomo College, Indatra. The class was really nice and useful for us. And the problems, which were a little bit tough for me, some of the problems only, and others was easy to catch up. And theory also.
Okay,
Hello.
Yeah, yes, Shubham.
Yeah. Hello, ma'am. Good evening. I am Shubham Jaiswal. I am integrated Ph.D student at Kerala School of Mathematics. Your session is really nice. I mean, with the tricks and tips. Now the questions becomes very easy and solved in less time actually. I mean, as according to what I used to solve in 2 to 3 minutes, now I can solve in seconds. Thank you very much. Yeah, thanks.
Yeah,
happy to hear.
I'm Harinar Mondal from West Bengal, and today's session is very nice, and there is a lot of question and many varieties, and we get many things which I didn't know before. Ma'am, can you tell us some group of linear algebra where I get the results, that's help me in IITSM or CSRNet? And I found that linear algebra is very good scoring in competitive exam, and there is not many part of calculation.
Okay, so when it comes to books, I think the most important text for NET exam is Hoffman's book itself, and Kumaresan and few other books. Hoffman is most important. I think it is taken as prescribed text for most of the universities. It's because it is mostly its syllabus is followed for exams. So better you hang on to that book, and yes, few other books, any which you feel like reading.
Let me add something. Of course, there are Sham series on every subject. In matrix theory, also you have Sham series. You can have a look at that. Many worked out examples will be there, and also there is one book. I'm not remembering the authors. Actually, that book is written by many people. Handbook of Linear Algebra. That consists of almost all the results in different parts of linear algebra compiled as a single volume. I'm not remembering exactly the publishers or editors, but I will try to share it through our groups. It's actually a good reference and an easy reference for preparing this type of examinations. Lots of results are compiled there without much proof and other parts, only examples and results. So, and also of course exercises.
It will be helpful for us if you share the link or any.
Yeah, I will try. I will check into that. Okay.
Okay.
So thank you, Harinarayan. So others also, please. Okay, your words will be really inspiring us to arrange this type of sessions in future, as well as for our resource persons also. Your comments will be really useful. You can, if you have any criticism also, that also can be mentioned, because they can also improve themselves. All of them are really budding researchers and teachers. So your opinions are most welcome.
Ma'am, I am Sindhu.
Ma'am, sir, can we get to... Okay, proceed.
Okay, Sindhu, you can continue.
Ma'am, I am Sindhu from Nandana College, Malingra. Now I am MSc first year student. The class was really fruitful for us, ma'am. Actually, your first class also we have attended, the limits and continuity. That also that's useful for us. Today's session also that very helpful for us to understand the concepts of this linear algebra. Ma'am, really thankful, ma'am, for this session. And you have included a lot of problems also. That also very helpful for us to write the jam exam. It is very near, okay, ma'am. See, we are expecting your more classes. If possible, you conduct some more classes for us. Okay. Ma'am, thank you so much.
Sure.
Vinod Kumar sir, thank you, sir.
Thank you, Sindhu. Sagar, you can.
I mean, sir, can we please get to know about your as well, like from which college you both are and what you are doing?
Yeah, sure. I've done my graduation from Mercy College, Palakkad, Kerala, and the post-graduation from Cochin University of Science and Technology. Then I have cleared CSIR NET in June 2020. I was having JRF with All India rank 122, and I have qualified GATE in 2021. Currently, I'm a research scholar at Amrita Vidyapeetham, doing research in graph theory.
Okay, ma'am. Thank you so much.
Yeah.
Any others?
Hello.
Yes, Lakshmi.
Hello, ma'am. Myself Lakshmi. I am a third year basis student studying at Maths College, Coimbatore, Kerala. This is the first time I am attending your live class. I have seen your recorded videos based on the topics limits and continuity, but this is the first time I am attending your live class about this matrices. And both your session and the problems were really useful to me, especially the topics based on the characteristic polynomial that I was not much aware of that how to find the solution, sorry, not solution, that how to find the polynomial using that simple formula. That shortcut method, I was not aware of that shortcut method. So thank you for explaining such topics. Thank you so much. Thank you, sir.
Thank you, Lakshmi. So, dear friends, tomorrow we have a session on TA for GS problems by Dr. Rahul Rajan. Tomorrow morning at 10 a.m. So, all of you are requested to attend that. And also we are having an online exam at 8:30 today. Yes. Any others have something to add? Tanmay?
Yes. Hello, ma'am. Thank you for this wonderful session. I'm Tanmay Karmakar. I'm currently an MSc student and first year student at IIT Madras. Thank you for this wonderful session. It was a two-way discussion from you and us. Thank you for this session, and thank you, Vinod sir, for this conducting this kind of sessions. I'd also like to comment on a question that you have solved. So should I go ahead?
Sure.
Yeah, go ahead.
Yeah, that question, P is a 4x4 matrix with entries
Conjugate pairs.
Yeah, it seems like I think we need that the entries are from the rationals for getting the last two eigenvalues. Is it?
I'll check and then let you know. Is that okay?
Yes, obviously. Thank you.
Okay, thank you, Tanmay. So I think, is there anyone else? Otherwise, we may wind up here. Okay, thank you, Nandana. If possible, we can have one more session with some more problems. If you have enough time during your research and all that, I know that you are busy with your PhD and all that. So if it possible, we can think about it. Anyway, thank
Sure,
you
sir.
for this, for your helps. Okay, thank you. Thank you, everyone. Wish you all good luck in your exams. Do prepare well. There is no other shortcut. Only, okay, you have to work hard. Then only the things will come into your way. So all the very best. Thank you. Thank you, everyone.